Hello everyone, this is video 2.3 on equivalent fractions. So we're going to be talking about uh, fraction equivalents, and we're not going to get into too much of what we're going to be doing with them when we get into sort of operations with fractions, adding, subtracting, multiplying, dividing. We'll do a little bit more of that, but for right now we're just kind of defining and building up models around equivalent fractions. So we should define what equivalent fractions mean. And what we mean by equivalent fractions is that there are fractions that represent the same number. Again, I'm coming back to the same idea of number versus numeral. The numerals are different. Symbolically, they're different. So we would know already that if we were talking about 1/2 and say 3/6, symbolically those are different. A 1 and a 2, a 3 and a 6, I mean, they use different numbers. So the numerals are different, but the number is the same. The quantity is the same. So they represent the same thing. If we think about the pictures that we talked about in the previous video, we could make our 0 here, our 1 here, and I'm going to make them the same length so we can see that these are to scale. So this would be 1/2. And then 1, 2, 3, 4, 5. So now this would be in sixths. So I can shade this in. And so I can see that my 1/2 and my 3/6, they represent the same quantity, right? So linearly, I could tell that this is the case. I'm not going to go through an area model example or a circular model example. If you want to see those, you can go through those. So I'll just use this one model to show it. But this is what we mean by equivalent fractions. This can be a little bit weird to motivate because we're going to establish what equivalent fractions are so we can use them a little bit later on. So a lot of the utility for this is going to come down the road. And so I never really like giving that you'll see later as an answer. That always feels kind of like cheating a little bit. So there's some things that we can talk about that certainly use equivalent fractions now. But I mean, if we're being really honest, a lot of the utility comes from a lot of the processes and operations that we look at later on. Uh, One really important point about equivalent fractions that I think really deserves some attention in classrooms is how many equivalent fractions are there? So we see that 1/2 is 3/6. Can we think of another equivalent fraction? So we could think of maybe 2/4. Can we think of any more? Can we think of any more? And so having students sort of like name these things through so they don't think that 1/2 has an equivalent fraction, but that they understand that there's an infinite number of equivalent fractions that are possible. And we need that flexibility because then it allows us to do a lot more operationally with these equivalent fractions. So I think it's a subtle point, but I think it's a very important point and one that deserves to be mentioned in doing this topic. So let's look at simplifying fractions. So it's kind of the process that I just looked at in the previous slide, but in the other direction. So if I were to have, so here's my 0 and here's my 1. So I'm going to do sixth again, but now I'm going to do 2/6. And so the question is, can I simplify this? Can I write this as another fraction that uses a smaller number of pieces? So rather than start with the symbolic process of saying, okay, well, I've got some A, B, and I'm going to divide that by some C, and so I get A divided by C over B divided by C, which is how I learned this at first, and probably how you learned this at first as well. But it's the abstraction without anything concrete to support it. Well, why am I dividing by C? Why am I dividing the numerator, the denominator? I don't understand what's going on. I can get an answer. I can certainly, divide both these by 2 and get 1/3, but I don't know what it means, and more importantly, from a pedagogical standpoint, I don't know what it looks like. So that answer has to be attached to some sort of meaning, or else it's just sort of devoid of any sort of context. So if I want to try to break this into 1/2, okay, well, is there any way I could color in 1/2 and make this the same as this? Well, clearly no. I only got 2 choices. I could do 1/2, which is too much, and if 1/2 is too much, then 2/2 is certainly too much. So we know that 1/2 doesn't work. I'm going to skip a third for obvious reasons. If I wanted to try to break this into fourths, I could break it like this. And now students should be able to tell. I mean, these are far enough apart. There's no way to think this is like artistic error. There's no way that this is going to work. So we can tell that 1/4 doesn't work. So I'll erase those fourth marks. They're not going to work. I could try fifths and try to get that to work if I wanted to try to draw 1/5. And the 1/5 might be a little bit easier to do in an area model, and we'll look at sort of an example of that here in a couple of slides. But fifth isn't going to work either. But now if I break this into thirds, so if I break this into thirds, then I can see that I've got 1/3 is the same as 2/6. Now, what we want in our math classrooms is to do examples like this and then have a student raise their hand and say, wait, can we just divide that numerator and that denominator by 2 and get our answer? When a student sort of uncovers or discovers this process, this algorithm for themselves, and in that moment they feel like they've created something new, and in a lot of ways they have. It may not be new to the world of mathematics, but it's new to them. That is infinitely more impactful than when we just tell a student what to do. Going through problems like this and putting students in situations where they can discover for themselves these processes, these algorithms, is infinitely more powerful. It's infinitely more impactful than just saying, okay, everybody sit down, simplifying fractions. Here's what we do. Take out your notebook. Here's our rule for the day, which again is how I learned a lot of this and how a lot of you probably learned a lot of this. But it's not good. It's just not powerful. It's not impactful. So that's what we're looking for when students do that. Now, you're going to have a lot of students who have maybe already seen this before, and so when they come in, they already know that algorithm. And so now we're sort of working in the other direction. They have the algorithm, but we need to put the concrete supports underneath it. They need to be able to see, oh, that's what that means. This is why I'm doing this. This is why this works. So when I divide the denominator by 2, I'm combining these pieces, right? So I'm going from 6 pieces to 3 pieces, and so I'm taking these 2 pieces and joining them together. And so now I have 3 pieces. And now the same thing's happening to the numerator. If I'm joining these 2 pieces together, then these 2 pieces here also join together and make 1 piece here. These pieces are being joined together 2 at a time because I'm halving the number of pieces that I have. And so when I'm connecting these pieces together, it impacts both the 6, which now becomes a 3, but also impacts the 2, which becomes a 1. So seeing this, being able to illustrate this, makes this algorithm make a lot more sense. I'm a big fan of being able to start with that concrete and build into the abstract, but it also works to start with the abstract, to start with the process, and then go back and put the supports in there as well. So yes, both directions work. Yeah. Okay. So finding a common denominator. Now, we're not necessarily going to be finding the least. We're not necessarily finding the least common denominator. We're going to talk about that a lot more in chapter 8. But for right now, we're just looking at a common denominator. And so suppose that we have a problem like we've got 1/3 and 1/4. And so we want to find a common denominator between 1/3 and 1/4. So we want to know what equal sized pieces could we have. And so this terminology can be a little confusing, so we may want to talk about it really in terms of what it's doing. So we know that the 1/3, we know that 3 equal sized pieces make up the whole, and then the 1/4, the 4 equal sized pieces make up the whole. Be really careful with problems like this. You see teachers sometimes where they'll take like a 1/3 and then they'll take a whole like this 1/4. And so then you get something like this where visually the 1/4 is bigger than the 1/3, and it's no good. So you want to try to make your wholes sort of as similar in size as possible, so the fractions all sort of make sense. This is 1/3 of a smaller whole. This is 1/4 of a bigger whole. We're making comparisons from in different contexts. It doesn't work. So what we're going to do, instead of using two different wholes for this, we're going to use the same consistent shape. So I'm going to draw a rectangle. So I'm going to break this into 1, 2, 3 pieces horizontally. So here's my 1/3. And then here's my 1/4. Now, it's worth our time to stop and make sure that students can still see the 1/3 and the 1/4, right? And again, students can be flexible with how they think about the 1/3. They can put in a bunch of L-shaped pieces, but we're going to really focus on these horizontal pieces and these vertical pieces in how we build the model. The interpretation can be flexible, but we built this a certain way because it has this regularity to it that makes it easier to draw. So look at all these pieces now. The question is, what is the common denominator? What is the size of this piece? So each of these individual pieces is what size. What's important is that this whole hasn't changed. The whole for 1/3, the whole for 1/4, and the whole for this question is the same whole. Everything's remained consistent. So this is going to be one piece. And now how many pieces of this size make up this whole, make up this entire rectangle? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, we want that moment where students say, wait, is it just 3 times 4? Do we just multiply the denominators together? Again, putting them in the position to see the concrete model and then abstract the mathematics out of that. That's what we're looking for. And so, yes, this is going to be 1/12. A common misconception to this is going to be that students are going to want to add the 3 and the 4. Some students, without looking at the model, are going to think 1/7. Again, if you have the model, you can say, well, where's the 7 coming from? Do we see 7 pieces here? Let's remember what we mean by denominator. And so once you build that understanding, students can look at this picture and see that clearly it's not 1/7. That 1/7 is from a flawed algorithm of I don't know what to do, so I'm just going to start adding numbers together. And realistically, if we just do the algorithm without this concrete picture, the multiplication looks as arbitrary as well. But by doing the concrete model first, the multiplication has meaning. It's not arbitrary. It's very clearly motivated as to why we do it and to how it works. Now, I want to point out that in this case, this is the least common denominator, but it's only because 3 and 4 aren't divisible by any of the same numbers. If I were to say, let's change this problem up a little bit, and let's make these 1/6. So if I now go through, and I'll erase this circle as well. So if I were to go through and put these lines in, so now these are all 1/6, right? So one piece here is going to be how much? Well, it's 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6. So we know that this is 1/24. But 24th is not the least common denominator of 6 and 4. 12 would be. And so the reason that this is not the LCD, like I said already, the 6 and the 4 are both divisible by 2. So that's why we're not going to call this a least common denominator. Um, Sometimes it might generate the least common denominator, but for the most part, we're just focused on being able to find this common denominator piece. Okay, this last problem type you're going to see a lot of on the homework, and we're probably going to talk about this a lot in class. And I really, really like these problems. And they don't really have a name, so I just kind of call them equal space tick marks problems, which just rolls off the tongue, doesn't it? Um, but they're all characterized by having a number line and wanting to use equally spaced tick marks to show some other number. And in a lot of cases, like, well, if you had a number line and you had 3/4, being able to show 1/4 would be a piece of cake because you're dealing with the same size parts. But if we have a problem like show 3/5 on a number line, and then we're going to use equally spaced tick marks to show 1/3. And so now you can see the issue that this is in fifths and this is in thirds. So it's going to be a little bit harder to sort of show where this is. Really like these problems. So let's start with show 3/5 on a number line. Now, we can just draw the 0 and draw the 3/5. If you want, you can go ahead and draw this out to 1. It's not absolutely necessary that you do it, but if it helps your students' understanding or if it helps your understanding, by all means, go out as far as you need. But we just need to be able to find this 3/5. And now, because this is 3/5, I want to show 1/5 and I want to show 2/5. And now this is bothering me that when I'm writing this, I want the fractions to either all be vertical like this or all be slanted like the first one that I wrote. So I'm going to be consistent and make this 3/5 like that. Okay, and so one of the things that can be a little bit confusing for some students when they see this 3/5, they're going to want to break this into 5 parts. And it's going to take some convincing for some students perhaps that no, this is 3 pieces, so I need 1, 2, 3. And so, like I'm saying, if that's confusing for some students or even for you, if you want to extend this out and show all the way up to 5/5, so you can see, well, there's 1, 2, 3, 4, 5 pieces, of which I want 3 of them. So you can see how the 3 and the fifth are working together in this problem. By all means, this is not, this part to the right, the 4/5 and the 5/5 are not necessary parts of the problem. Anyway, so we want to show 1/3 on this number line. Some of you probably really want to decimalize this problem. That's not what we're going to do. There's a more precise way of doing this. What we need is a common denominator. And so if we want, if we need to, we can come over here to the side and do what we did in the previous problem and find what our common denominator is. So I can break this into fifths this way and then thirds this way. We're going to pretend these are all the same size pieces. And so I can see that my common piece size is 1/15. That's my common denominator. Again, by almost sheer coincidence, least common denominator. But we're not so worried about that. So what this tells me is I want to do this problem in 15ths. This is a really important common theme to a lot of working with fractions. The biggest obstacle in doing these problems while we can't do them is that the pieces are different sizes. And so if the problem is being a different size, then the solution is make them the same size. So once I convert everything into 15ths, this problem becomes a heck of a lot easier. So now I'm going to make this 15th. And so I had 3/5. And so 3/5 when I broke it into thirds became 1, 2, 3, 4, 5, 6, 7, 8, 9, became 9/15. And again, we can talk about how this is multiplying by 3, multiplying by 3. It's that equivalent fraction process by doing multiplication instead of division. But there's a physical picture to it as well. I mean, there's a way to make this make sense. And so now the 2/5 was 1, 2, 3, 4, 5, 6 15ths, and now this is 3/15ths. And we can see we're counting by threes. So here's 1/5, 1/5 is 3, 2/5 is 6, 3/5 is 9, so on, so on, so on. So now let's put in the rest of our tick marks. So this was 3/15ths. So here's 1/15, 2/15, 3/15, 4, 5, 6, 7, 8, 9. Students hopefully will start to understand, well, when we broke this into thirds here, that's why this got broken into thirds here. It's the same idea, it's the same process. And so now we just need to figure out where 1/3 is. So 1/3 would be how many 15ths? So we're going to, here, let's do it this way instead. So we'll do 1/3, and now we're going to multiply by 5, and get 5/15. Or we could come down here and look at our rectangle. So this was my 1/3, which I can count to be 5/15. So I can see from the model that the 1/3 is 5/15. I can see from this algorithm that it's 5/15. But really what I want are these two things to work together. I want these two things to work in concert. And so now I can see this is 5/15. So I just count 1, 2, 3, 4, 5. Here's my 1/3, which is 5/15. There's my answer. 1/3 and there. Really, really like these problems. Expect to see quite a few of these. Really the important point that I wanted to make in doing this problem, like I already said, this idea of when the parts are different sizes, moving them to where they're the same size, and the way we do that is by using equivalent fractions. So your checkpoint problem, we're going to pour 5/6 of a cup of water into a bowl, and they want to scoop out half of a cup of water. Be careful with this. We don't want to scoop out half of the water that's in the bowl. It's a really easy way to misunderstand this problem. So I don't want to cut 5/6 in half. I just want to take out half a cup of water. And so how much water is left in the bowl? So draw a picture to show how much water would be left. You're probably going to put in the 5/6 and then show the 1/2 being removed. We're talking about subtraction without ever saying the word subtraction. We're saying the word subtract, but this is a subtraction idea which will get us into the next chapter. Draw a picture to show how much water is left, show that process, and then give your answer of how much is left. And so, yeah, we'll leave this. If we have any questions about this, we'll talk about it in class, or let me know. Thanks.